So here's what we have so far. Cauchy's integral theorem. So we've got a closed contour integral where f is differentiable in, and I could also write analytic probably, since that's what we're gonna call it now. So f is analytic in and on that contour, in and on C. Okay. Then the next really interesting fact is this: integral dz z minus z naught to the nth power closed integral around z minus z naught equals r. This is one that's just good for practice. And what we do is we let z equals z naught plus r e to the I theta. You guys got a question?
So.
We got this. Okay. So we're about to do, so I'm just reviewing what's key here. The dz equals I r e to the I theta d theta. Right, we're just doing a circle around this point z naught. And now we have I r e to the I theta d theta. And the z minus z naught to the nth power is r e to the I theta to the nth power. And this turns into 0 to 2 pi, and you get something really interesting. Okay, if n is equal to 1, everything cancels here except for the I, and you get 2 pi I. Okay, so n equals 1, and if n is not equal to 1, you've got an integral that ends up, that just turns into a 0. So this, first of all, this fact, and then this kind of amazing fact there leads to the Cauchy integral formula, which is 1 over 2 pi I integral f of z dz z minus z naught. Same thing, except in this case, f of z naught or 0, and this is z naught in C, and this is 0 if z naught is exterior. So yeah, this is just by way of review. So our strategy for a number of interesting integrals now, and just, this is the z squared plus 1. This is the prototypical integral that we're always evaluating. It has poles at plus and minus I, and you just circle this pole like that, and you're gonna, this actually has this form here. The strategy that we keep using now is we want, as r goes to infinity here, we want this semicircular integral to vanish. Okay? And then the integral that we're actually doing, minus r to r, taken to infinity, the integral that we're actually interested in on the real axis is simply evaluated by knowing the integrand at the pole. Okay? So this we've done a few times now, we're going to do it several more times. But the current question is, what are the conditions for this semicircular integral to vanish? And at the moment, we just needed at least 2 powers of z here in the denominator. Okay, but we can can do more with that. Okay, so we're looking for the condition for semicircle integral to vanish. So far, if we have enough powers, if you have 2 powers of this or higher, we're in good shape. So what comes next is something called Jordan's lemma. And yeah. And then I had some extra homework problems. I'll add those later. Okay. So Jordan's lemma is next. Okay. If C sub R is the contour Z equals R e to the I theta, 0 less than or equal to theta, less than or equal to pi. Okay, so this is just the upper semicircle as, come to know. Then we have this estimate, magnitude of the integral e to the iz dz less than or equal to, take the magnitude signs inside the integral, that's a standard integral of the magnitude, e to the iz dz, just take the magnitude of everything inside the integral, and that is less than pi, okay? So that's the lemma, that's the statement that we want to prove here. And the proof, and again, we're doing this big semicircular integral, so we gotta pay attention there. So the proof's gonna go like this. We have to just do an estimate of e to the iz. E to the iz is equal to e to the I, and now this is our z here, our e to the I theta. E to the I, and then r cos theta plus I r sine theta equals e to the I r cos theta e to the minus r sine theta. Okay. So what about the magnitude of these? Well, and let's do dz is equal to I r e to the I theta d theta. Okay. So the magnitude of these, blue here, same here. So what do we have for magnitudes? R cos theta, or real e to the I, that's just one. So here we have equals e to the minus r sine of theta, and that's always going to be positive, so we're good on that one. In this one here, you have I is equal to, let's even do this, magnitude 1, also magnitude 1. So this is just, magnitude of this one is just d theta, r d theta. So this equals r d theta. So now you see what we're going to do. We're going to plug this into here and try to get an estimate. So far we have e to the I z dz over this c sub r is equal to e to the minus r sine theta. We've got an r d theta 0 to pi. So what we have to deal with is the fact that we want r to go to infinity, and the question is which one wins, e to the minus or the r there, as we integrate those. So we're doing an estimate on this, and this was an estimate on this right here. So we're going to do an estimate, and here's a useful sketch. We go 0 to pi over 2, 0 to 1, and there's our sine, okay? And we can compare that sine to the straight line. So the slope of the dotted line, is 1 divided by pi over 2. Equal to 2 over pi. So because this is an e to the minus r sine, we can say e to the minus r times this function is less than e to the minus r times that straight dotted line. Okay. Because we're, in the negative something larger compared to that. So that's what we're going to do. We're going to replace r sine theta by r times that dotted line there. Let's free up some space over here. And then the integral is no problem. So we have this is star. We continue here. This star we still have equal to 2, 0 to pi over 2, e to the minus r sine theta, r d theta. And now we can make that substitution equals 2, or less than or equal to 2. Here we go. 0 to pi over 2 e to the minus r. Now here's that replacement, theta divided by pi over 2 r theta. So now we've got 2r 0 pi over 2 e to the minus 2r over pi theta. Now we just have to do that exponential function, 1 over negative 2r over pi. So we'll evaluate that, take the limit as r goes to infinity, and see what happens. r goes to infinity, we're just left with the 1. Okay, so r goes to infinity, this gets arbitrarily small, 1 is left over, and we're just left over with pi. Okay, so that's an interesting one, and this is really useful. Okay, so what is this useful for? Let's remind ourselves what we just showed. Okay, so we have integral this thing, radius r, e to the I z dz. Less than or equal to pi as r goes to infinity. So this is the kind of integral we have when we're doing our Fourier transforms and integrals. Okay. All those e to the I kx's are going to be of this form, and that's how we're going to get Fourier integrals to behave well. Okay. So let's get an example up there now. Actually, very important. I can put a homework. So we have this proof right here, and what we need is the bottom half plane as well. So you can actually repeat the proof in its entirety, show that this integral here, e to the minus IC dz, for the bottom integral, okay, this one here, less than 5, r goes to infinity. Okay. And you can do, so this is a funky thing there, but let's go ahead and write down what the exact thing would be. So here we would be talking about z equals r e to the I theta. What thetas would we be talking about now? We're doing the bottom circle, the bottom half, the bottom semicircle. You could say theta, you could say pi less than theta less than 2 pi. So yeah, before we move on, make sure we see what these two statements are. So make sure you have, everybody have this here. So you're going to want to go over this calculation really carefully for the top half. And we're going to need both of these for the following reason. There are times when we have to complete our integral around this curve, and there are times when we have to complete the integration around this curve here. And it really depends on what you have up here. You have e to the IZ versus e to the minus IZ. Because if you were to complete e to the minus IZ around the top half, you would get a divergence. You get something that goes to infinity, but it's literally the same proof with a little change of variables will get you the statement for the bottom half, for the bottom semicircle. So Jordan's lemma we need in both cases, and you can already see if you remember, just for your memory here, if you had f hat of k equals something we've been doing recently, right? You had this integral f of x e to the minus I kx dx, right? This would be the type of integral that you would have to complete around the bottom half. And the other half of the Fourier theorem we complete around the top half. So that's where that's going to come into play practically right away. It's kind of an important lemma for doing all these integrals. So you take the proof I just did and you really basically just have to do a change of variables and it should all work out. Good, so now I have a bunch of interesting problems we can tackle. I'm just going to list them and then we'll draw the line under which ones go for this week and which ones go for next week. So we now have
eight for this week, including some tests.
5 for this and then 6. A couple of them are really small though. But that's good. We'll draw a line under them now. So I think we can do Jordan's lemma for this week too. We'll draw a line under them and then I'll start adding the other ones for next week. That's reasonable. Okay, we'll do an example. This is just for perspective. Okay. Okay, let's see. I've got a good example over here. Example that will make use of this. So we're going to do this integral from 0 to infinity cosine ax x squared plus 1 dx. So the first step we'll do is we'll take the symmetry of this thing and we can say that that is 1/2 of minus infinity to plus infinity cos ax x squared plus 1 dx. Okay. And that's going to be 1/2 of the real part of the IZ dz over z squared plus 1. Now here's where there's an important note. You could write in the cosine, let's put this as a note up here. You could have said cos ax, and we did this before, is equal to 1/2 e to the iax plus e to the minus iax. Okay. But if you did that, you'd have an integral where you actually have to go around top half on one part of it and bottom half on the other, because you would have these two different e to the z's, okay? So in a case like this, if you just say it's the real part of this e to the iz, you make no mistake. There's a pitfall there to be aware of. And not just z, but IAZ, and I'm taking a to be positive. Okay. IAZ. dz. Okay, what we have now is by that previous lemma we just had, we have something that's going to be well behaved when we so that was the point, because we have the z squared plus one and we have the estimate on the e to the I, see. So we're in good shape there, and we can write it's 1/2 integral let's do some period here, and then we'll write the following. But 1/2 integral e to the I ac dz d squared plus 1. Make our standard factorization here, e to the I ac z plus I z minus I. We're going around z equals I, so we're gonna have that 1/2 2 pi I e to the I a times I. And in the denominator, we went around this pole, so we have times 2I. And we end up with pi over 2 e to the minus a. That's nice. A goes to 0. We're back to the one we've done before. The larger A is, of course, the more the thing is suppressed. Good. So I have one in my notes here that I'm not sure if we had on the homework or not. So I'm gonna write it down and see you guys if we had this one as well. We have this one, x cubed plus 3, no, x squared. X squared plus 4. Did we have the one with that in the numerator?
No.
We just had the one with that straight.
Yeah.
So yeah, let's add this one to the mix as well.
Is that this week or next week?
That'll be for next week. Everything after this is for next week. Okay. Okay, so this is giving us a little more applications. Now we want to do some implications of Cauchy's formula that are going to take us to the complex Taylor series. So yeah, we got a few steps to go on that one. What we're going to get that goes beyond Taylor series we've seen before is we're going to get series with the inverse powers as well as the positive powers. So these are implications of Cauchy's formula. Of the Cauchy integral formula. And it's going to lead to expansions of this form here. F of z equals sum over a sub k z minus z naught to the k. That looks just like a Taylor expansion, right? Except we're going to have all powers from minus infinity to plus infinity. So when you do this, it's called Taylor and a Laurent series. Okay? Okay, so we've learned all about Taylor series with the positive K, but we're also going to have the negative K. You know, we've seen a lot of already in our examples. We've got these negative powers in our integrations. So this is where we're headed to, and we have to work our way into that. This and this, these are big problems. So we start with Cauchy's integral formula. 1 over 2 pi I integral f of c dz z minus z naught k equals f of c naught. If c naught is inside the contour, 0 otherwise. Okay. So we're starting with that, and we now want to take derivatives, and I'll just, we got our picture here. That's the positive contour, and we've either got z naught inside, or we've got z naught outside. What we're going to do next is take a derivative of this in terms of z naught. So derivative so f of z naught plus delta z naught minus z naught divided by delta z naught. Right? And then we'll take the limit as delta z naught goes to 0. So what we have here, because we're viewing this thing as a function of z naught, right? We're inside there. Good. We've got this minus this, and so we'll pull out a 1 over delta z naught. I can put that outside, in fact. I've got 1 over 2 by I. I've got 1 over this delta z naught. And now I'll just do the difference of those two integrals. So integral f c dz. You'll notice the z naught is only here in this argument. So z minus z naught minus delta z naught minus integral f of z dz z minus z naught. And if we look for a common denominator, we've got, you know, z minus z naught minus z minus z naught minus negative, therefore plus delta z naught. So when we look for a common denominator, we're just going to have a delta z naught in the numerator. It's going to cancel that one. Okay. And so we get 1 over 2 pi I integral. That one's already been canceled. F of z dz z minus z naught minus delta z naught times z minus z naught. Okay. You know, if I wanted, I could have put the delta z naught here and here, and then shown that they and strike them. So good. This is where we started. That's the definition of the derivative when limit delta z naught goes to 0. We struck it from the numerator and denominator. So the only place it is here. And that can just be safely taken to 0 because we're taking z naught to be a true interior point inside this thing. So the deltas are arbitrarily small. We can take that to 0 And we end up with 1 over 2 pi I integral FC dz z minus z naught squared. Now what you'll notice is the result here is the same as if we had just differentiated under the integral. Okay. So that, if we had just taken this thing here, differentiate with respect to z naught, we'd have pulled out an inverse power at -1 and then another minus sign would have canceled that. So that's satisfying to realize it would have, it was well defined either way. So we have, make sure we write this down now, so now f prime of z naught is equal to 1 over 2 pi I dz f of z minus z naught squared. And then by induction, we can just keep doing it. We'll just get higher powers, and then we'll generate the entire factorial. So by induction, f nth derivative at z naught is equal to n factorial 2 pi I integral f of z dz z minus z naught to the nth power n plus 1. Right, first derivative was 2, nth derivative n plus 1. So these are the facts we're going to use to get our Taylor and Laurent series. And you can see these inverse powers are playing a big role in those series expansions. So there was F, and it's always an interior point, and because it's a true interior point, okay, you can do all these limiting processes, no problem. Good. So if you look at it having done this, you see you've got that function. It's as though you just kept taking derivative with respect to z minus z naught. Z naught. And everything well behaved, well defined. Okay. I'm going to erase all this. Okay, now we're going to look at something familiar. So let's recall 1 over 1 minus z sum over z n equals 0 to infinity. For magnitude of z less than 1. We're going to use this to construct a Taylor series. So this is a bit of a tricky contour, but we'll just start with our formula. And when we write this, we always mean we're around an interior point, okay? And we write f of zeta d zeta. Zeta. Z just changed variable. labels, because now, such a change of labels. About a point z sub 0. So if you ignore the right side here and say, okay, we have f of z, we want to expand around the Taylor series around point z sub 0. You're looking at just what we've been studying this whole time. We've got to do a construction here, though. And there's our z sub 0. Z is going to be on this contour, and zeta is going to be on the outer contour. These are all circles for the moment. So because of that, we have zeta minus z naught is greater than z minus z naught. These are just concentric contours. Here we go. Okay. So we've got this formula, which I'll repeat. So now we've got the f of z equals 1 over 2 pi I. Zeta, d zeta. And we're going to bring in f of zeta d zeta. Zeta minus z naught minus z minus. So you can see the z naught minus and plus cancel, so this is still an identity. Equals 1 over 2 pi I integral f d zeta f of zeta minus z minus z naught zeta minus z naught zeta minus z naught. Okay, multiplies out zeta minus z naught minus z minus negative plus z naught. Okay, so zeta minus z, and this cancels that denominator there. But because this is larger than this, I'm going to draw this in blue. We have we can do this infinite series right here in this integrand. Okay, so we're just going to do this infinite series for this expression here, okay, which is less than 1, this entire expression there. And it's going to generate what we're looking for. So let's put that down and study that. I gotta erase this slide. So we're using this one, but I'm just erasing it down. Okay, here goes. Equals 1 over 2 pi I closed integral f of, so e zeta, f of zeta, zeta minus z naught, sum over z minus z naught to the n zeta minus z naught to the n. this summation, zeta minus z naught comes out there. Equals, now we're just gonna switch the order of those. Sum over z minus z naught to the n. And what's left here, 1 over 2 pi I integral f of zeta d zeta. So we pick those powers up again. So zeta minus z naught to the n plus 1. What's left here is just the derivative divided by n factorial. So this is n derivative at z naught divided by n factorial. So you see we've got the form of the Taylor expansion there. So we've got the f of z equals sum over f to the n of z naught n factorial z minus z naught to the n. So what's amazing is we had all n and infinite derivatives, and what we began with in this whole process is just the existence of one derivative. Okay, so these complex functions have infinite differentiability if they have a single derivative, a complex derivative. Okay, and otherwise it's a very standard form here. Now this is not the series with the inverse powers yet, but we're going to get to that as well. See, I'm going to put that as a note here. The thing with the blue bracket, that's where I made use of that standard series. So the punchline here from f of z is differentiable. We obtain infinite, all infinity of the derivatives. Infinite differentiability. Okay, so that's what that signifies, among other things. Okay. What I'm going to do next is just write down the Laurent series. And then I'll return to its proof next time. So I want to. Okay, so good. We have this. That looks just like the Taylor series. So let's write down the Laurent series so we can look at it. So the Laurent series is going to look the way I just said, and as a compact form. So we're going from negative to plus infinity, a sub n z minus z naught to the n. So right, the Taylor series would be the positive powers. The a sub n is going to be 1 over 2 pi I. It really extends this formula. F of zeta d zeta. So this is when you're circling that point z naught to the n plus 1. C. I'll explain the tilde later. It's slightly different picture. Notice what we have. Looks exactly the same, except it extends to the other powers as well. Okay? Extends to the negative powers. Okay? So it's a very natural continuation of the Taylor expansion through all powers And so the poles that have been playing such a big role are gonna be covered in this series here. So we got that Laurent series. I'll just give a quick example of one and then we'll call it good. Let's see. Okay, so we got that formula there. That works, yeah. See, that contains both of these now. So we're going to expand this function here, 1 over z times z minus 1. And what we're gonna do is just pull out a negative 1 over z, and we've got 1 over 1 minus z. And what do we have here? Negative 1 over z, and then we know the series expansion for this thing. Z to the n equals 0 to infinity. And so we have minus 1 over z, 1 plus z plus z squared and so forth. So we end up with minus 1 over z minus 1 minus z, etc. Okay, so that would be the Laurent series around, right? We keep getting all the positive powers expanded around 0. So this is expansion about 0, z equals 0 for z less than 1. Okay. What about z greater than 1? So we just have to rewrite this thing. For magnitude of z greater than 1, we can do the following. F of z equals, we're going to factor out another 1 over z. Okay, so we have 1 over z, we factor out another 1 over z. We're going to put 1 minus 1 over 1 minus 1 over z. Okay, and so now you can see we're going to have the convergence because magnitude of z is greater than 1. So we'll have 1 over z squared. And what is our sum going to be here? Negative 1, or not negative, 1 over z to the n equals 0 to infinity. Now we have 1 over z squared, 1 plus 1 over z, and so on. Z squared, 1 over z cubed, z to the fourth, and so on. So you'll notice this was the same function. But it has a very different series expansion depending on where you're expanding, what the values of z are. Both of these, by the way, have been expanded around the origin. Okay. Good. That takes us far enough for today. Anything else? Yeah, one more thing. So these are the terms that we're always referring to as poles, right? So we have different singularities. This function here just had one of these singularities, this one has a whole bunch of them. So what we'll do is we'll learn to deal with those next time. And then we'll come back into our integration theory. Okay, good.